how do we connect snowflakes, fractals, the brain, where's this all start?
So we're going to have a look at fractals. First of all, we have to define what the heck is a fractal. That's the first thing we need to do. I'll show you some examples in nature, and then I want to try and connect that to pretty recent research that's been going on in terms of what are called neuromorphic structures, trying to have devices, trying to have computing architectures which are much more aligned with how our brain computes, and perhaps more correctly, much more in line with how our brain is wired, and the ability for our brain to make new connections, to be plastic, to make different connections. There's a whole burgeoning, really developing area of research which is incredibly exciting in terms of trying to take that type of process and that type of dynamic and embed it in sort of inorganic systems. As we said in the last video, what does a computer do? Well, it takes in information, it does something to that information and outputs other information. Sort of what we do. We take in a huge range of sensory inputs, we do something to them which results in some output, we do something, we feel something, etc. So it's a question about how that information is processed, and of course we don't have CMOS up here. We don't have incredibly regimented and well-organized, top-down, sculpted pieces of silicon that do all the processing. Up here we're a mess. I'm particularly a mess. But if you look at the structure of the brain, it's incredibly branched and incredibly dendritic. Lots of different pathways. If you look at a nerve cell, you look at a neuron, very fingery and very branched, etc. Almost random, it looks like. Certainly not like a very rigid, grid-like type structure as we have with CMOS. So the question then is, what's happening in terms of just how the brain processes information? And of course, you have incredibly good, incredibly powerful pieces of silicon technology that can, outperform us in so many ways. But then you ask it to distinguish between a chihuahua and a blueberry muffin, and it gets completely screwed. So where we win out. So what is it about how we process information? I'd love to say we're going to address that question. We're not quite, but we're going to certainly look at the role of sort of fractal and dendritic structures. So basically, what is a fractal? What is a dendritic structure, and why are they important in information processing? First year student here in physics at Nottingham, Noah Hardwicke, came in, give me a Christmas card, which was very, very nice of him. But what I didn't at first realize is that this is a computer-generated Christmas card. All the code is in here, and moreover, it's unique. There is no other Christmas card like this. You'll have much the same structure on other Christmas cards, but it'll be very slightly different because all of these features, the snowflakes, the ferns, the trees, are fractal in nature. And he's generated them with a piece of code, and every time it'll be slightly different. So it is truly a unique Christmas card. So I was very happy to get that, not least because Sean and I had been planning this video and it was a very timely Christmas card to get. Snowflakes are incredibly interesting. This is a paper from 30 years ago, I believe, 1987, from 30 years ago. There's still a huge amount of debate as to how snowflakes form, what is the underlying structure. But what's important in this paper and in a number of subsequent papers is that they've used a very simple, or relatively simple, computer simulation to model just how snowflakes grow. And running in the background here is a simulation called a diffusion-limited aggregation simulation. I didn't write it. It's actually written by one of the first-year students here again, a guy called Jamie Mair. I do a lecture just at the start of the first semester when the first years arrive, and on chaos and various different aspects of chaos. And one of those is related to fractals, which we are getting to slowly. And Jamie, I mentioned in the lecture, well, if you really want to understand something, code it. And that's exactly what Jamie did. And he's developed this simulation whereby what you have is lots and lots of little particles. They could be water molecules or ice particles, for example. They're moving around, and we have a really simple rule. Basically, it moves around, it follows a random walk, which just means it's equal probability of going north, south, east. Is that right? No, east, west. And so it follows that around. It's also called a drunkard's walk because you're just stumbling around all over the place. And if it hits another particle, it sticks and it doesn't disconnect. And then what happens is that sticks, and then the next particle moves around, that sticks, and that sticks, and that sticks, and that sticks, and it becomes very higgledy-piggledy. But what's interesting is it becomes very higgledy-piggledy, but with a very specific type of structure. It's random each time we run it, but the overall characteristics and the statistics are the same time and time again, and it's called a fractal structure. If you look at it, you see this branching, and if you look for these patterns in nature, you find them everywhere. Obviously ferns, trees, riverbeds. A great deal of it stems from the work of Mandelbrot, and many of you will have heard of the Mandelbrot set. The important thing here is why is it called a fractal? So fractal is actually short for fractional dimension. So what does a fractional dimension mean? So we've got a line. Okay, you can move in that direction back and forth. It's one-dimensional. If you've got an area or square, it's two-dimensional. If you've got a cube, three-dimensional. The problem is, what about this? It's not a close packed structure. It's not a line, but then it's also not a closed volume or a closed area. It's somewhere in between the two. And actually, if we work it through, we find that it can be defined in terms of having a fractional dimension, somewhere between 1D or 2D, or in other cases between 2D and 3D.
I'm looking at that and saying, to me, it looks like it's a 2D structure, that.
So it's a 2D structure, but how do we actually define this dimensionality? It's a special type of dimensionality. It's a very good question. So what we need to do is think about just how we break this structure down, or just how we would form a structure like this or any other structure from building blocks. So let's take a line. And I've run out of room. Let me start again. You might need to cut an awful lot of this out, Sean, we'll see.
Phil.
Ruler. Thank you. I'm getting it.
Without wanting to cut to the punchline, but is this going to be about how many blocks it takes?
Exactly. So this is all about scalability, and it's all about a concept which is basically self-similarity. And that's very important when it comes to fractals. So here we've got a line, and we can break that line up into, well, as many pieces as we like, but let's just keep 3 for simplicity. So each one of those is exactly the same shape. It's not only self-similar, it's identical apart from a scaling size. So how many pieces have we got there? We've got 3, and we've got 1 dimension. Similarly here, now we've got 2 dimensions, but we're going to divide this up into a series of blocks. We've got 1, 2, 3 in that direction, 1, 2, 3 in that direction. So we've got 9, and that's 2 dimensions. Here we've got 27, and that's 3 dimensions. Now we can see a pattern here. 3 is fairly straightforward, is equal to 3 to the power of 1. 9 is equal to 3 to the power of 2. There's our dimension. 1 dimension, 2 dimension. 27 is equal to 3 to the power of 3. So there's our dimension. Okay, so that's fine. Those are usual objects. We're very familiar with those. How do we do what is that? How would we write down its dimensionality? What's the self-similar bit? So we could start with that, but let's not. One thing we could do is we could measure the ratio of the perimeter to the area. That's certainly one way of doing it. Those objects are pretty well defined and boring, incredibly boring. We're going to look at something called the Koch snowflake. I'm not going to try and measure this out because it'll just take too long, so just bear with me. I'm going to use a pencil in case I make a mistake though. So we start off with an equilateral triangle, and then what you do is you again divide this up into 3, and you put another triangle in there. With that's now your side length. So these are all equilateral triangles. And then you put another one over here.
Oh, so you're just losing the lines?
Yes, we're just losing the lines. So largely because what we want is to have a continuous line. So now having got rid of those, there's our first generation snowflake. Then you do the same thing again. Divide this up into 3, put your equilateral triangle in there, and then similarly here, and here, and here, and here. Repeat, 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 repeat. And what you end up with is something that is pretty well drawn on the wiki page. Start with a triangle, do that, break it up again, break it up again, break it up again. What's remarkable is that now, if you follow this process through and keep going, the line length here never converges. So what you'll end up with is an infinitely long line in a finite area, which is a fairly, compared to these very boring objects, which are finite, both in length and area. Here we have something which is when you extend it out and you kept going with that process, you'd have an infinitely long line in a finite area. The important thing is that the perimeter length doesn't converge. So it really is, if you followed this to its natural limit, what you'll end up with is something that's infinitely long, but it's in a finite area.
So looking at that, you're saying that's constrained in an area. Is that because it kind of like the angles work so that it just keeps working back on itself?
Exactly. So it's confined. It's not diverging out of that area. It's constrained within that area, just exactly due to the geometry. And now we could work this through if we just take this. So if we look at that relationship, what we have is that the number of pieces, n, is equal to the scale factor, s, because what we've done is we've taken this and broken it down into 3, to the power of the dimension. So the number of pieces, in this case 27, is the scale factor, because we broke it down into 3 in all 3 dimensions, to the power of 3. For this one, n would be equal to 27. This is going to be a long video, Sean. Jeez. S is going to be equal to 3. That's our scale factor. And D, our dimensionality, is going to be equal to 3. Now we're going to have to do some maths or math, depending on which side of the pond you're living. What we have here is n is equal to s to the power of d. Now, if we take logs, some of you might remember logs, what we'll find is log n. And one of the wonderful properties of logs is that raising to a power becomes a multiplication in log land, is equal to d times log s. Does that make sense, Sean?
Right, so log n.
Yeah, log of the number of blocks is equal to the dimension times the log of the scale factor. Okay,
good.
This is going somewhere. Let's put that up here. Right, so that's fine for these. And when you work that through, you find out that, oh, well, let's actually go the next step. Just one more line of maths. To work out what d is, let's divide both sides by log s. So log n divided by log s, divide here by log s, we obviously remove the log s. And what you find is if you work this process through, and I encourage you to do so, then you find that you will get an integer value for the dimension. What happens if we do it to the snowflake? So we start off with a line. Now we're going to divide it up into 3. And then remember, we take our equilateral triangle. And if I can draw that correctly, we put that equilateral triangle there. And then we get rid of that. But the important thing is we've taken our line and we divided it in 3.
Does it matter that that's made that line longer in?
No, it does. And you're not jumping, well, you are jumping the gun, but you're jumping the gun in an exceptionally good way, because that's exactly where I'm going. Okay. So we've divided it in 3, but we've actually got 4 units now. So 1, 2, 3, 4. Remember, this is an equilateral triangle. So we've divided it in 3, but we've got 4 units. Make sense? So now our n is equal to 4, but our s is equal to 3. Now, good, you're nodding. I like when you nod. So that means that d is equal to log 4 over log 3. We've decided that what we're going to do in terms of how we're going to make this pattern is we're going to have a scale factor of 3, so each individual line is a third of the original length, but we're just going to set up our geometry, so we need 4 of those lines.
Right. Okay.
And if you work out then what the dimension is, you'll find that that's something like 1.2. It's not an integer, it's a fractional dimension. So that's fractals, that's where it comes from. We haven't had to do too much maths, but we've done a little bit. But as you can see, the beauty of maths, the beauty and power of maths is you get so much out of it.
So if we went then to the next level, we would obviously put a triangle in the middle of here.
But we're doing the same process again.
And would that increase it?
No. So it's the same process time and time again. So you only have to do it at this level, because you're asking yourself at each level. And the important thing is it's self-similar. So you can look at it on a gross scale, and then you can zoom in and zoom in. Overall, you're going to see the same structure. So now we've connected the snowflake, wonderful festive snowflake, to the mathematics and the computing. Let's explore that in a little bit more detail, because when you look for these fractal things, they're right across nature. In fact, as physicists, what we tend to look for is very ordered, and I'm a physicist, I'm sort of interloping here in Computerphile, but I'm definitely a physicist. We tend to look for very ordered things, very structured things, crystals. We spend so much of our life thinking about crystals and how atoms are incredibly well ordered, etc. But in fact, if you look across nature, that's not what it's like at all. Those incredibly crystalline structures, we're not crystalline. If we were crystalline, we'd be incredibly boring. If we were crystalline, then you wouldn't have the randomness that you need for evolution. You wouldn't have the randomness that you need for information transfer, etc. So crystalline and very ordered structures are the exception rather than the rule, which makes these type of structures fascinating.
So fractals can contain more and more and more. I'm trying not to use the word data, but I'm going to use the word data in one same contained area. Is this something we can use for memory?
So that's a fascinating question. Thank you for that, Sean. That brings me to this wonderful structure. Some of you might be familiar with this. It's called the Mandelbrot set. I hope some of you are familiar with it. If you're not familiar with the Mandelbrot set, just stop listening to me drone on. Go and look it up. Go and spend a few hours. So I'm not going to go into the details of the algorithm. Wiki is actually, again, pretty good in terms of the Mandelbrot set. And if you Google Mandelbrot set, you will find beautiful image upon beautiful image upon beautiful image. This is what it looks like, and it's actually a process that happens on the complex plane involving imaginary numbers, but we don't need all that detail. Important thing is that you have a grid, and at each point in that grid you do a particular algorithm. It's a particular, you set it up in a while loop, and you keep that running, and you basically let that run until it reaches a certain limit. And what you find is that when you do that process, you get this incredible structure. You get all this complexity coming out of an algorithm which involves nothing more than squaring a number and an addition. That's all it involves. And yet you get all this incredible complex detail. So complexity from something very straightforward. That would be good enough. You look at this and it's incredible. You can see the sort of almost snowflake dendritic structure again, the branching. It's a mathematical landscape. And then if you zoom in to this particular region, I've just taken that at random, you start to see a little bit more like the snowflake structure. By the way, this is a piece of code I wrote using something called LabVIEW a number of years ago. In fact, I wrote it so long ago I couldn't find the original code. And it also gives you an idea of just how disorganized I am. But we zoom in again and look, snowflakes everywhere. We see the same type of fractal structure, and we can keep going. And we can keep going, and we can keep going, and we can keep going. Forever. Forever. It never stops. As long as you've got enough computing power, you can do this till the end of time, and it will never stop. Yet, you can code it in 5 lines. If you're a better programmer than me, probably 3 lines. It's remarkable. So when you think about that in terms of information, if we were to take every individual pixel here and try and encode it and store it, we need vast amounts of memory, but we can capture that in 5 lines or less. It's mind-blowing when you think of that. So finally, how does that all connect back to the brain, which is where we came in? Back in physics world in March, you can see coding and computing. We're finally starting to get computer scientists and physicists to talk together a heck of a lot more than they used to do. There's a great article in here, a number of great articles, but there's Jessamine Fairfield, who used to work in John Boland's group in Trinity College in Dublin, is now in Galway. See, the article's called Smarter Machines. And she talks about the work that she was involved in Boland's group in Dublin, the work that she drove. So usually when we think about nanoelectronics, when we think about trying to get faster capacities and more computing power, we think about being very regimented and very controlled in terms of how we have ordered structure on the surface, and we use lithography and billion-dollar plants to really do this very, very fine machining. What they do is they sort of chuck a load of nanowires. They take a solution, not that different from this, put it on a surface, let it dry, and you get a higgledy-piggledy net or mesh of wires all connecting against each other. And again, it's an open structure. It's not incredibly close packed. Lots and lots of different connections that can form. And that gives rise to really fascinating properties, including the ability for the network to rewire itself. And that's something our brain does. Our brain is incredibly plastic in terms of forming connections, and it also has a multitude of connections that branch off, much like the sort of fractal structures we've been looking like. There's the question of whether the brain is fractal is, again, something that's been debated at length time and time again, but it certainly has that large range of different connections that we don't have in the type of technology, silicon technology, that underpins so much of our world. Our brains are sort of more along these lines. And they call this neuromorphic, a neuromorphic device, because it's mimicking the type of, or hoping to mimic, the type of process that happens in our brains.
Looking at that picture and the way you've just described it, they're creating wires in some sense, but without any purpose, not any purpose, but they're just a bunch of wires and they don't know what they do.
Precisely, yeah. So instead of...
Is this like my wiring cupboard, which is full of old phono leads and things, and if I just put some power in it, hopefully it might start thinking?
Perhaps I wouldn't be that extreme. If your wiring cupboard becomes sentient, you're on the way to a Nobel Prize, let's put it that way. Just keep quiet about it. But don't let it get too sentient, that wouldn't be good.
This is like a ground-up way of producing something, rather than being an architect and saying this is where the foundations will be.
Here's what I've got, I will work with that. That's exactly it. So instead of being constrained by, I need to put this here, and I need to have this interconnect here, and I've got to worry about leakage, and I've got to, how will that fit with the particular blueprint I have? Let's throw away the blueprint, just throw some stuff down, and let's see, well, what function does it give me? And if it doesn't give me a function, well, let's move on to the next one, throw some more stuff down. And that's a refreshing way to think. It's not an engineering way to think, it's more a biological way to think.
It's hard to understand that this would ever work at all.
It does some remarkable things in terms of they can train, not just this group, but a number of groups across the world. You can train these things to recognize certain pulse sequences, for example, just in terms of what they're being fed in terms of signals. So it's very much in its infancy. In fact, there's, although it's very much in its infancy, there's a massive project which has created and generated a huge amount of controversy called the Human Brain Project, which is an EU-funded project, over €1 billion.
We have interviewed Professor Stephen Ferber about the Human Brain Project.
Wonderful, so let's put a link down there.
Yeah, and using 1 million ARM chips was the thinking then. I don't know where that's gone, we haven't...
Yeah, it'd be worth to check with them, but I know they were thinking about a range of different strategies and possibilities, and I think, as far as I understand, that one of those was a little bit more along the lines of this neuromorphic approach. I could be wrong. I'm sure I will be corrected at length and repeatedly in the comments section if I am wrong, and I look forward to that very much.
This is a bit orangey. Let's not critique me too much. So yeah, they're very different to the originals, and the important thing is that we don't know what went into here. Right? We know G, but we don't know A, and we can't find
information which is comparable to the type of effects we have to consider when we're thinking about black holes.